Hi, my name is Mahan-Percivall. I'm a distance education graduate student with the Soil and Water Sciences program. I'm going to be talking about mass and volume relationships because early on that really confused me and I thought perhaps maybe somebody else might need some clarification. I really liked the picture that our professor pulled out of the textbook that showed the relationships between air, water, and solids. And this particular picture shows the relevant proportions of volume and mass. But what I didn't get or understand was the connection between measuring the mass and the volume and getting something like total porosity. But if you remember that porosity is a portion, it's a portion that includes the air and the water components of our soil core. The solid fraction is also a portion, and it consists of the solid component of our soil core. If you look off to the sides, you can recognize that these can be measured with mass, or they can be measured with volume. So we call these portions phase fractions. So the air phase fraction would then be the volume air over the total volume in the soil, and we wouldn't be left with any units because the two units for volume would cancel each other out. So really we are looking at a portion or a percentage, but we call it the phase fraction. Similarly, the water phase fraction is the volume of water over the total volume of the soil. Now the reason why I circled this is because this particular portion of the equation becomes really relevant later. So I'd like you to note that theta V, or the water phase volume fraction, is equal to the volume of water over the total volume of the soil. So far I've talked a lot about the volumetric water portion or volumetric water content, but I haven't talked about the gravimetric. So the gravimetric water content is the fraction of the soil that's water versus the fraction of the soil that is solid. However, in this case, we're taking the measurement using mass or weight instead of using a volume extracted. So the gravimetric water content would then be the mass of the water over the mass of the solid components of the soil. And that would give us the fraction of water per solid unit. The next step might get a little bit confusing if we didn't remember that density is simply a relationship between mass per unit volume. So we technically could rewrite mass as a relationship between its volume and its density. And that's what we see here. Here you see the volume of water multiplied by the density of water would actually be equal to the mass. But we're just rewriting it this way for right now so that we can rearrange the units a little bit. Over here you see that we've done the same thing with the density of the solid particles, or the bulk density, and the volume of the soil sample. The really cool thing that's happened here now is that, sorry I lost my mouse, is that the volume of water over the total volume of the sample could now be pulled out of the equation, and if we pulled it out we'd have the volume of water over the volume of the sample, and that gives us the water phase volume fraction. So there's our relationship between the volume fraction and the gravimetric fraction. Now how are they related? Well, they're related by their densities, that component that's left behind. The other cool thing is that the density of water we know is 1. The density of water is 1 gram per cubic centimeter. So we technically could pull that out of the equation and we'd be left with our major relationship here, which is our gravimetric water fraction is equal to our volumetric water fraction divided by the bulk density of the sample. I borrowed this slide from Decagon Devices because I loved the way that it showed the relationship between volumetric water content and gravimetric water content as this bridge between the two being bulk density. Now, why is it that we would take gravimetric water content when for most of our measurements we need volumetric water content? I think it has to do with mostly that it's just easier. So it's easier to get a full sample of soil, evaporate the water out, and then check the mass difference or the weight difference instead of trying to suck all of the water out and get a volumetric determination. If your brain is still fighting this like mine was, here I put it down one more time where you can actually see the gravimetric moisture content related to the bulk density, and the density of water then gives you the volumetric moisture content, which is the volume of water over the volume of dry soil. And if you look here, the volume of water over the volume of dry soil is equal to theta V, which is our water phase volume fraction. In the lab, you took the gravimetric measurements for the water content in the soil. You did this by drawing out the soil and using the difference as your gravimetric measurement. You were also able to calculate the bulk density of the soil by determining the dry mass over the total volume of the soil. What's really important about this is now you can use that dry bulk density and the gravimetric moisture content to determine the volumetric moisture content. Once you determine the volume of the solid particles within the soil, then you are now able to determine the total porosity, the particle density, and lots of other parameters that would help you characterize the soil and make predictions about nutrient flow, water flow, etc. Thank you so much for joining me, and I hope that I was able to clarify the relationship between volumetric fraction of water content and the mass fraction of water content, and how we can use the relationships between those two measurements to characterize a soil.